So we're an hour into it, and we're going to do our featured segment now, and that is basics of multi-rotor helicopters. We started the show back in October, and we were so motivated to do the best show possible with this killer content. We skipped right over all the basics and stuff. So that's what we're going to do tonight. We're going to start 2016 with a quick overview, and this is also going to serve as the launch for our group build 2016. The group build, what we're all building this year, is a basic FPV quad. Now, you could take what we're doing and do it on the scale of a racing quad, like a 180 millimeter or a 250 millimeter racing quad. But what we're talking about is something more along the lines of a flame wheel, like an F450 or an F550, and the ability to carry both an FPV camera and maybe a GoPro so you can record the flight, or a Mobius, or what's that other one called? The Legend, I think, from Foxeer. So an action camera, an FPV camera, maybe a stabilization gimbal, so a little bit more lift than you might have, or a little bit excess lift for some of these extra things compared to what you might have with your typical FPV racing quad. So that's the goal for the group build. So this first review, what we're going to do is we're going to look at all the parts, and then what we're going to do is we're going to trace the electricity out of the battery through the helicopter and talk about how that distribution works to get all those elements of the helicopter power so they could all do their part and make their contribution. So real quick, let's look at the parts. I'm going to put my glasses on. It's going to make a little glare. So what we have in a basic helicopter, and when I start, you're going to say this can't be true, but it is true. All these different components that I'm going to talk about are typical for any helicopter. Any helicopter might have differences in terms of specifics, but they're all generally using these components together as a system to make the helicopter. Whether it's a small one like this, my old MQX, which I still love to fly, this little Kodo, this little, let's go off to the side, Bill. This little Kodo is a micro quad, and there's some differences here from some of the bigger ones, brushless versus brushed motors, but this one's slightly larger. Slightly. This is a frame. This is a frame that I designed. I mention this from time to time because people say, "What's up with that funky frame?" That's my own. That carries a DJI ZenMuse H3 3D, so it's a GoPro 3 with a 3D gimbal and a DJI A2 flight control system. That helicopter is using all of the components that we're going to talk about here. So once you understand this stuff, it isn't so much a matter of can you build one for yourself anymore. Now it's just a matter of what is it that you need to build to satisfy your goals. Okay, so first we start off with a frame. Now the frame can be anything from, my good friend Mike down in Houston used to love building quads with towel rack bars from Home Depot. Those metal square tubes that you get with the towel racks, they're paper thin metal, and they're super cheap, super lightweight. He used to make frames with them and they worked great. He used to go out and do photography with them all the time. But I've got a couple frames here, and this is the one I'm going to use for my build. I'm using the Hobby King version of the F550 hexacopter. I'm actually going to build it as a quad with my little XY frame layout. But when it comes to frames, man, just about anything will work. So these are the frame plates. These are the frame plates, right? These are the arms that bolt in. But you know what? This could just as easily be a piece of plexiglass with some square wood pieces that you might have ripped on a table saw, or you might have bought them off the shelf at Home Depot or somewhere. And the motors, so long as you screw the motors to it, you know, to hold it in place well enough, a frame does not have to be a $1,000 investment, okay? The frame can be something that holds all the components in place, doesn't allow an unnecessary amount of vibration to go through and to mess up the camera placement or the video quality. But there are a lot of options from inexpensive to very expensive, and homemade is always an option if you happen to be handy. So don't get too carried away with the frame selection, okay? Now, with the frame, the next thing that you would have are motors. Now, with these helicopters, there's a couple differences that are basic, okay? These are brushless motors, and you know they're brushless motors because there's 3 wires coming out of them, okay? Brushless motors and brushed motors work pretty much the same way. They both have an electromagnet, and here's a much larger one. This one's from this is about a 25cc gas engine equivalent. It's a Turnigy motor that I bought for a profile RC plane. So most of the time, these have a little spring clip down on the bottom that keeps them together, keeps them from coming apart. So I took the spring clip off before I left the house today so I could pull this apart. Ah. Thank you, Bill. That was great timing. I'm glad you found that entertaining. Anyway, so here's the motor. This is the bell, it's called, and these are the windings, or this would be called the armature on an older brush motor. But what happens is you have permanent magnets in the bell, and you have electromagnets in the armature, or the poles. And what happens is these windings are activated in a sequence that causes them to repel these magnets. So when this is all put together and it's running, these things are very high speed, switching on and off, pushing the magnets, causing the motor to turn. Now with a brushed motor, the same exact thing is happening, except the armature sticks out a little bit and there's segments around the shaft, and the electricity is being fed to these different coils via brushes. The brushes are a conductive material that rides the ring and delivers electricity to different parts of these inner windings in order to sequence the power and make the motor turn. Now this is all kind of complicated. It's hard to explain with fixed things here without like some sort of sample video, but we'll talk about this at the website. If you have any questions, we can go into it. I can throw up some YouTube links where these things are explained more completely, but most of the time your smaller quads like this are actually going to have brush motors, and you can tell because there's 2 wires instead of 3, okay? So these both have brush motors. Brush motors, unfortunately, wear out. They're not as long-lasting, they're not as powerful as brushless motors. But for small quads like this, man, they work great. They make enough power. They work well with the battery power that they fit into these. So as a whole system, they're great. This thing flies awesome. I challenge anyone not to tell me that this thing isn't still a pisser to fly in a gymnasium or something. So brush motors versus brushless motors. Most of your small, ready-to-fly quads, the really small stuff, is going to be brushed. The stuff that you're going to build that's going to be a little bit larger is almost always going to be brushless. So brushless has 3 wires, brushed has 2 wires. Props. To build your helicopter, you're going to have 2 different propellers. One set is going to turn clockwise. Excuse me. The other set's going to turn counterclockwise. And when half of your motors are turning one way and half of your motors are turning the other way, when all of that spinning mass is balanced, the helicopter will sit stable in the air. When one half of those props are turned a little bit faster than the others, the helicopter is going to torque in reaction to those spinning props. So the yaw of the helicopter is actually controlled by these different turning props being sped up or slowed down depending on the direction that you're trying to yaw. So when you buy your props, you're going to buy half of them as clockwise, half of them as counterclockwise. There's all different blade designs. And if you're getting started with your first build, if you're joining us for this group build, you might say, well, I don't want to waste a lot of money on props. You know, get over it. You're going to waste a lot of money on props. I've got boxes of propellers at home, 3 blades, wood, carbon fiber, plastic, orange, black. I'll have some green ones by the end of this year, I'm sure. But so the props are something where a lot of it is trial and error. A lot of it is getting recommendations from other people online, especially at a high-quality website like multirotorforums.com. But just to give you an idea of what you're looking at in terms of differences, I really like Zor wood props. They have a nice blade profile. You know, they're not too thin. They're not too, you know, this is a real wide, this is the cord. The line from the front to the back is the cord. So this is a really wide cord prop. Something like this is a very narrow cord prop, okay? The line, the distance from the front to the back is very short. These are very thin. The blade profile is thin. So this prop right here doesn't make lift so much by, or this prop doesn't make a pushing force so much by lift created by this airfoil. This thing is just kind of beating the air into submission and displacing air more like a pump and forcing itself through the air. Something like this prop that actually has a little bit of thickness to the blade, it actually has a nice airfoil profile to it. This is actually making lift like a wing, like a sailplane wing or any other airplane wing, and it's actually creating a propeller force by lift. They're all doing that, but some do that more than others. something like this is making a lot of lift. It's a slow fly prop from APC. These are popular with little sport flying helicopters that aren't doing real heavy lift. So I've also got this big propeller, just in case you can't see. This is from an 80cc gas engine, but again, has a nice blade profile, nice thick cord. So this prop is going to make a lot of lift. It's going to be efficient at doing it. Never let the price of the components discourage you. If you want to fly and just get out there and experience this hobby, there are always going to be components that you can use that will get you flying. Don't worry about buying the most expensive stuff. Don't worry about buying the best stuff. There are a lot of low-end components that work great, that are going to give you a ton of fun, and are going to allow you to learn and develop and be ready for when you might be able to buy some of those better components. Okay, so after the props, we have the batteries. Now, we're just going to talk about lithium polymer batteries. Lithium polymer batteries are all the same as far as the chemicals, the chemistry, what's going on inside the battery that makes it produce electricity. And because of that chemistry, the individual cells, they don't really design the cells. Nobody goes to the lab and says, today I'm going to design a cell that makes 3.7 volts per cell. Nobody said with NiCads, hey, Bill, why don't you go in the lab next week and design a cell that makes 1.2 volts per cell? And Bill came back and said, oh, I found the perfect combination to give you 1.2. No, they do the chemistry, and the chemistry is what dictates the voltage that each cell is able to produce. So with a lithium polymer battery pack, these individual cells are able to make 3.7 volts, and that's a nominal thing. They make a little more when they're fully charged, a little less as they're being depleted. But what we have, and this is important to understand, there's cells and then there's packs. So an individual cell looks like this little rectangular thing. Let's go to the side view, Bill. See if we can see that. Okay, so this is a lithium polymer battery pack, and it's made up of 3 individual cells. Now, some people think that the Chinese don't make high-quality products, but somewhere in China is a factory that makes the world's strongest double-sided tape I've ever seen, and they use that to put these cells together. So this pack is 3 cells that are taped together, and if you've ever tried to pull these apart, it's almost impossible to do it without damaging the pack. This battery pack is actually completely dead, so I was able to rip this apart and then mash it back into shape, and I'll throw it away after this show. But I just wanted to show you that even this big brick of a battery, it's a 6-cell pack, it's 11,000 milliamps, which is a high-capacity, higher voltage battery pack. This thing is made up of individual cells just like these that are 3.7 volts each, okay? And then this is a smaller pack like what you might have on your FPV racer or in some of your foamy park flyers. They're all the same chemistry, so all of these are making 3.7 volts per cell, and then they make higher voltage packs by putting more cells together, wiring them up in series, which means one battery goes into the next, that one goes into the next, and by putting them together in series like that, they get higher voltages. So those are your batteries. And I should just say real quick, batteries are always going to have, multi-cell packs are always going to have the power leads, which are the heavier duty wires, usually with a heavier duty battery connector. And they're always going to have this other multi-wire plug, or tap we call it, and that's going to be for charging the packs. Most of the bad reputation with lithium polymer packs catching fire when they're charging comes from when they first hit the market, when the chargers were trying to charge them like any other battery pack with just a couple of leads hooked up to the main power wires and charging it like it was one big battery. What happens is these individual cells, some of them, they're not identical no matter how well manufactured they are. Some of them, this cell might take a charge a little bit faster than this other cell. So when the pack just keeps getting charged and charged and charged, some of these individual cells might charge up first, and then they start to get hot because they're being overcharged and they catch fire. So the way they've gotten around that to make these packs a lot more reliable and useful for different industries and us in the hobby business, they have what's called a balance charger. So the balance charger actually uses this tap with the multiple wires coming out of it, and it charges each cell in the pack individually so that it's monitoring all the cells and it's monitoring the voltage of the cells, and it's monitoring them to the point that if one cell is taking a charge better than the other ones, it's going to limit electric to that cell, and allow the other ones to catch up. So it's balance charging the pack, which is a huge, huge advantage if you want to keep your house, your car, your pets from catching fire during the charging process. These batteries are very dangerous, and if we're going to talk about basics of multi-rotor helicopters, you should know right off the bat, these batteries are dangerous. Okay, you shouldn't keep stacks of these things fully charged in your house. After you're done flying and they're discharged a pretty good amount, just leave them like that. They're better off that way anyway. They last longer. But if they come back damaged, if you wiped out and you know, the corner of the pack is damaged, or it's perforated, or they're really heavily puffed and they get hot when you use them, stop using them. Damaged cells, puffed cells are a fire hazard. Don't put them in your house, and always charge on a hard surface. Always charge where there's access to a door or a window. You would not believe, I took a battery pack, a 6,000 milliamp 4-cell pack, and I took a pickaxe, and I said to my son, hey, watch this. And I put the pickaxe through the cells. It immediately started smoking, and it is unbelievable how much smoke comes off of these packs when they're shorted out like that and when they're damaged and they catch fire. The thing burned for 40 minutes. It was like a smoke bomb in my backyard, and the smell was the most toxic thing. I mean, I've smelled burning epoxy, carbon fiber that, you know, I touched with a heating iron by mistake, so it burned the epoxy and the composite material. This stuff is the most toxic thing I've ever smelled. If this caught fire in your basement and you're saying to yourself, oh, I'll be able to get down there and carry it outside, you'll be dead before you make it back to the steps. They're that bad. So that's my warning. I hope that saves somebody the grief of having to deal with a battery pack on fire. So next we go to the flight control. Got my little box of goodies here. The flight control is a board that has a computer chip and then sensors. It has lots of plugs attached to it. It has some mounting holes. And what you're going to do with that is fly your helicopter. Now, this is an old Hoverfly Pro board, which makes a great display board because it's so big. Newer boards are smaller than this. And basically what this is going to do is it's going to run firmware in these little computer chips. That's just like the computer sitting on your desk or your laptop or in your car. It's going to run the firmware. It's going to sense the motion of the helicopter, and it's going to control all the motors individually. That's how these things fly. They fly because these motors are being controlled by this flight control board or by a flight control board. And the ability of that flight control board to manage these motors individually is what allows it to fly. So if this helicopter, and I call it a helicopter, some people on YouTube like have a thing about calling it a helicopter. It's a multi-rotor helicopter. So in order to avoid saying multi-rotor helicopter every single time, I say helicopter. It makes sense, but people on YouTube are flaming me saying, it's not a helicopter. It's not a helicopter like single rotor, it's a multi-rotor, colloquially known as a helicopter. There's a word, we'll look that up, we'll link to it on the site. But anyway, so what happens is when this thing is sitting here hovering and it's not moving, that's because it's in equilibrium, it's balanced. Each of the propellers is making the same amount of lift. It's making it nice and flat or level, so it's not going to move. Now, if you want it to move this way, you have to lean it forward a little bit, right? And to do that, it's going to speed up these back props. It's going to slow down these front props, so there's going to be a little imbalance. And as it leans forward, as soon as that thing takes an angle, it's going to start going in that direction. So if you want it to go backwards, the flight control board is going to speed up the front motors. It's going to slow the back motors, and it's going to lean it backwards. And as soon as it starts to take on that angle, it's going to start moving. Now, when it starts to move, if it's not a real sophisticated flight control system, it might start to descend because now it's not making as much lift in the vertical direction, so it's going to start to descend. So you have to add a little power. But the flight control system is managing each of these motors individually. If you've never flown one of these, if you've never had one in your hand, if you've been just amazed at what they do, that's how they work. The flight controller, via these different sets of pins, each pin set is going to a different motor controller, and they're all being controlled independently. And some flight control systems are good for 6 motors, some are good for 8. There's some flight control systems out there that are flying 12 or 16 motor helicopters, and they're doing it well. They've got a lot of processing power on board. They've got great firmware. But that's the basics of how it works. So there's a lot of other things that would go into a helicopter build, and I'm not going to go into every single one in detail. We could talk about it at the website. We're going to talk about all this stuff as we continue to do the group build. But real quick, the thing that gets everybody hung up is power distribution. You hear us talk about, oh, I'm going to get a power distribution board for this build. What that means is they're going to get a board that looks something like this. This one's pretty old, doesn't have a really high power capacity. But what it does is it allows you, and how it's made real quick is it has a metal layer on top, a metal layer on the bottom, and they're separated by what is called an insulator in electricity speak. And that just means the insulator doesn't allow electricity to pass from the top layer to the bottom layer. And what it does is it allows you to plug the battery into this board and then distribute the power to different parts of the helicopter that need electricity, like your motors, like your flight control system, like your LED lights that flash and blink so it looks like you're a little cop car quad running around the park or whatever it is. So this power distribution board, that's a very common word that you hear. This is where people's brains lock up. They say, Bart, I understand motors. Your little demonstration with the MQX, that's cool. I understand the flight control system has sensors and it's all being run by software. But like when you tell people now the battery has to power all these different things and you have to come up with some way to do it, their heads explode all over their workbench. And they just, you know, we don't all come from these, I don't come from an electrical background. Do you come from an electrical background, Scott?
In the studio somewhat.
Oh, you're lying. He made that up. No, so it's power distribution, taking the power from the battery, from the big thick wires that are delivering the power into the helicopter, and then distributing it through increasingly smaller wires to where it has to go. Now, this is a harness that I had made for a helicopter a while back, and this is another option for power distribution where you take wires and you bare sections of them, you wrap them together and solder them, and then you put insulation around it so that you could plug in your batteries and then run wires out to where, this is when I was mounting motors on the ends of the arms. I was using this loom or this harness to take the power from in where the batteries are out to the arms, out by the motors.
A lot of people call that a squid.
A squid? I've never heard of squid.
Because it looks like a squid.
Ah, I guess it could.
The key is like the power distribution is the hub.
Yeah, it's
a hub, right?
It's a central point where the power is applied and then distributed out to all the different parts of the helicopter. Here's another example of one. This is a really small one by Microcopter, and it also has I2C distribution, which is a microcopter thing for the motor controllers. But you could see it's small, and it's 2 layers of copper, one on the top, one on the bottom, with an insulator in between, so there's no shorts. You attach wires to this. It makes a very clean, very easy installation, easy to wrap your head around. Now, what are we attaching? We're attaching ESCs. This is the last part of the puzzle. The ESCs are mandatory for brushless motors. In the olden days, those of you that had shops that did mechanical work and stuff, you know you could take a motor, hook it up to a power supply, and it'll spin. It'll spin at full RPMs being directly connected, whether it's a motor on your car, a motor in the shop that was for some power equipment or something. So brushed motors, you can apply power directly to them and they turn because it's the brushes and the segmented collar around the armature shaft that actually handles all the timing, sequencing power on and off, making the motor do its thing. Brushless motors don't have that luxury. Brushless motors are basically useless, right? There's 3 sets of wires. There's no brushes. They're basically useless unless you have this electronic gizmo to sequence the power through these windings. So an ESC is an electronic speed controller, and this is mandatory for making a brushless motor turn. Now, when you look at the wires on this, there's power input wires, right? The red and the black, those are 2 wires. That's where you apply power to the ESC. Not surprisingly, there's 3 wires that hook up to the, let me hold it off to the side here so you can see it. There's 3 wires that go to the motor, right? Motor has 3 wires, ESC has 3 wires. And then there's this other wire that everyone says, well, what's this one for? This is a 3-conductor lead, so it has 3 wires to it, white, red, and black. Different manufacturers have different colors, but there's always going to be a ground. There's going to be a signal wire, which is the white one, and then there's going to be a power wire in the middle, the red. Now that power wire may or may not be carrying power depending on the type of ESC. That's another little catch, little gotcha. Opto ESCs, as they're called, are not going to have power in that red wire. We can go into that some other time. So let's take a look at this from the perspective of an electron coming out of the battery. Where's it going to go through the helicopter, and what's it going to do on its way? And I think that will help you to understand how all of this stuff works. And then you'll be able to go forward and start planning your first build, maybe with us as part of our group build 2016. So here's the helicopter, right? The multi-rotor helicopter. It's got a camera mount. It's got LEDs on the bottoms of the arms, right? These little dots are LEDs. You can see them better on this one where they were actually cut out. Okay? And it's got a video transmitter down here. Has a second receiver for the camera mount, so it can be operated as a two-person rig. Okay, it's got motors out on the arms where they belong. It's got props. The flight control system is a DJI-A2 with a GPS. Okay, so let's take a look at where the electrons are going once they leave the battery. Okay, so again, here's our battery, and it has the power leads. Okay, the main power leads are where the power comes out and then goes into the helicopter. From the battery, it's going to go to some sort of a power distribution system. And that power distribution system is where the big wires progressively go to smaller wires. Different parts of the helicopter are going to need power in different ways, and this is one of the most confusing parts also, is that every part on the helicopter might not need the same rate of power. It might have different amperage requirements, it might have different voltage requirements, so you have to be sure when you're sending power to a particular component, it's the right power and it's enough power. Okay? When you have a harness like this, we have big wires where the batteries connect, giving way to progressively smaller wires as we go out closer to the motors, and as it splits again for two different ESCs, the wires get smaller still. Anywhere along here, you can pull full battery voltage just by tying in and tapping in with smaller wires. You could take something like these that are on this board, solder them into place on these two wires, and right there you have a tap for a regulator for LEDs, something for your FPV gear, whatever it is. So there's a lot of options when it comes to power distribution. So the electrons come out of the battery, out the main leads, go into the power distribution system, and then go out to different parts of the helicopter. The biggest draw from your batteries are going to be your motors. Okay, so from the battery, power distribution, it's going to go to your ESCs first. And again, the ESC, this is a big one for an airplane, so I just have it for an example. The most power is going to go to your ESCs. And the ESCs have heavier wires accordingly because they have a big power requirement. And then to the motors, they're a little smaller usually. And this lead, again, is going to go usually to your flight control system, because while this is the power in, this is the power to the motors, which is making the motor speed happen. This is the control system from the flight controller, which is telling the ESC how fast the flight control system needs the motors to be turned. So the white lead here and the white wire, the signal wire it's called, is actually sending all of the control information from the flight control to the ESC. And each ESC is controlling each motor independently. So just looking at my notes here for the ESCs are always going to get full battery voltage in. They're always going to apply full battery voltage out to the motors, but it's going to be sequenced is what determines the speed. Now inside this ESC, there's something called a regulator. So if this battery is 22.2 volts just coming down the pipe here, the regulator in here is actually going to knock that 22.2 volts down to 5 or 6 volts usually. Sometimes the ESC allows you to select that voltage. Sometimes it's fixed in the ESC. If it's fixed, it's usually going to be 5 volts. If it's selectable, it's going to be 5, 6, maybe more, depending on the ESC. But what happens is there's a regulator in here, and the voltage in this red wire is coming from that regulator. And what that's going to do, excuse me, in some cases, it's going to power your flight controller. In some cases, it's going to power the receiver for your radio control system. Got one of those in here too. So here's the receiver for the RC system. It's going to get power sometimes from that voltage regulator that's built into your ESCs. So the power is coming into the ESCs. The ESCs are sending the sequenced power out to the motors to make them turn at the specific speed that the flight controller is calling for. But then power is also going from those ESCs to the flight controller, to the receiver, to power that so that you actually have control of the helicopter. Okay, now, as far as the motors go, we talked about 2 wires versus 3 wires. We said they're pretty much useless without the ESCs. Brushless motors were pretty innovative when they first came out because they're so light and they make so much power for how much they actually weigh. Just like the batteries, these things were a giant step forward because they make so much, there's so much energy stored inside of this battery compared to nickel metal hydride or NiCads, which were the older generation packs. Yeah, so that's it for the ESC. Regulated power comes out, full battery power goes in, and then also full battery voltage goes out through the motor wires. One of the precautions, both of these motors will turn a 10-inch prop really well. This one weighs a lot less than this one, especially when you consider that there's potentially up to 8 of these on an octocopter. So don't get in the habit of thinking more motors better. These motors do get heavy after a while as you get bigger and bigger. They become less efficient also when you're asking a big motor to turn a little prop. So keep in mind that you want to design for the specific helicopter that you're designing. So from that power distribution system, there's a lot of other things that are going to need electricity, and this is where it generally gets complicated. You might have, here's a list that I have, you're going to have power for the flight control system. Sometimes it's going to come from the ESC wire. Sometimes it's going to come from the batteries for the flight packs because the flight control board will have its own regulator built into it. So you have to check with the equipment that you're planning on using. Sometimes with some flight control systems, Hoverfly, it worked really well to have a separate battery powering just the flight controller. FPV cameras, Scott talked about it a couple of episodes back. They all have different power requirements. So some might want 5 volts, some are going to want 12 volts. Some of them accept a range, 7 to 22 volts. They're able to do that because they have their own little voltage regulator built in. Whatever you put in, it regulates it down to whatever it needs for you. Your RC receivers are typically going to run on anywhere from 4.8 volts up to about 6 or 7 volts. There are newer ones that run at higher volts, so just check your equipment. And if you see a theme developing here where I keep saying check your equipment, that's because you have to check your equipment. Video transmitters. Usually the video transmitters run on a range of power because they have regulators built in. And let me see what I have here as an example. I have this small one. This is from like an FPV racer. And this one takes, I believe, anywhere from 7 to 24 volts. And then it has an output. No, this one doesn't have an output. But it does have a regulator built in, which is what allows it to take that range of voltages. I forgot to grab the other one. Just real quick, I keep talking about voltage regulators. These are 2 voltage regulators that you might find in the course of building multi-rotor helicopters. This one is from Castle Creations. This is a 10 amp. They call it a BEC because it's a battery eliminator circuit, which means if you're running one battery, you happen to need a lower voltage. You don't have to run a second battery. You just run a little regulator and you wire this up and you tune it in using a multimeter and it gives you the voltage that you want. This one, widely available on eBay for about $1, is a regulator. Pretty bare bones, but it works great. It's tunable to the voltage output that you want. These are lovingly referred to as buck converters because they cost $1. All right, you buy them by the dozen if you're going to buy them at all. All right, LEDs use power. You might have servos on board for a release mechanism, depending on what your application is that you're building your helicopter for. You also might have retractable landing gear, which is a servo mechanism that raises and lowers the gear in order to get the landing gear up out of the way for a helicopter with a camera mount that's able to pan 360 degrees. So these all require power, and this is where it starts to get ugly. So this is what I recommend, and then we're going to be wrapping this up. Scott's got a long drive home. So here's what I recommend. You start to hash out your equipment. Okay, you start to get an idea of what it is that you want to do and what you're going to need to do it. You make a list. On the left-hand side of your list, you write in. On the right-hand side, you write out. All of this equipment, whether it's a camera, a transmitter, a flight control system, all has voltage requirements going into the equipment, and they're all going to have some sort of signal or output that you're going to need to send somewhere else, like your camera. The camera is going to take power, but then it's going to send a video signal to the transmitter. So a good way to understand all of this is to first list the components that you want to build or that you want to include in your build, and then go down the left side, the ins, and say, what does each thing need in the way of power or signals in? Make a list. Some things are going to say full battery power, like your ESCs are going to get 4S or 6S voltage. Some things, like your video transmitter or your flight control system, are going to get a reduced amount of power. It's up to you as the designer of this to decide where are you going to get that power from. We're not going to talk about that. We're not going to answer all those questions right here, right now. But I'm telling you, you need to be prepared as you're preparing to do these builds. You need to be prepared to answer these questions. And we'll help you at Multi-Rotor Forums. I hope as some of you are coming to the site and finding it to be a good resource, I hope you're out there helping each other. But by mapping out all of your components and then what they need going in and what they need going out, it's going to make it all start to make a little sense because you're going to see there's variations. It's not as easy as you thought sometimes maybe to find 5 volts on your helicopter to put into the video, to put into your FPV camera, for instance. Okay, so moving forward with our group build 2016 at the website, the thread is already there. We've already been talking about this. Some of you have jumped ahead, and that's good for you guys that you've been able to get information from the website and from each other and be able to get your build started. Some of you are already flying, I think. But we're going to do this. We're going to build the helicopter first, and we're going to incorporate, what's going to make it different this year at least, is we're going to incorporate the FPV gear, and I'm going to make a series of videos to explain all of this, and I'm going to do it in much greater detail than I'm doing it right now. This is just an introduction, not just for our group build, but for people that are also maybe coming across this for the first time and saying they're interested, but they are clueless as to how all this stuff works. So the last little bit of the puzzle that we need to explain real quick is the actual radio control system, because that's what makes the magic happen, really. So this is a JR system. It's a system I've been using for years. It's been very reliable. And this is almost identical to this, which is an old Futaba system. And you know it's old because it has this big long antenna attached to it. So this is a system that was used before the 2.4 gigahertz systems came along. They're almost identical. The software is different. The quality of the gimbals has evolved a little bit, but you see switches, you see knobs, you see the 2 sticks. The system that these run on is called PWM, and it's almost identical in this one as to this one. There's little things like resolution, the number of steps from one side of the stick to the other, little details like that are different, but it's still basically the same concept, digital proportional radio control. So what this does is it has a number of channels that enable you to control an aircraft. And your helicopter, right, here's your basic MQX, an old Blade, I think it was. Yeah, Blade. This thing, the 4 basic channels of control are tilt or pitch, right, front and back, roll, side to side, yaw, which is like this, and then throttle, which allows the motors to spin faster or slower for climbing, descending, whatever. And those are the 4 basic flight control channels. Now, there's additional needs from your radio to be able to control the helicopter. If you have a gimbal, you might have a tilt control, you might have a shutter release. Depending on the complexity of the flight control system, you might have different modes. There's manual modes, there's auto flight modes, there's GPS modes, there's carefree mode, there's a switched fail-safe option on a lot of flight control systems. You can switch between cameras if you have multiple FPV cameras for a front view or a back view. All these different functions require channels for control. So it's not unusual to see people flying multi-rotor helicopters with 16 channels, 18 channels, or higher even. And this is a basic 9-channel system, which gives me a lot of options for control. And I've been able to live with this. I haven't had to buy a higher channel system. But figure for a basic multi-rotor helicopter, you are going to want at least 5 or 6 channels. If a buddy of yours that flies RC has a system like a Spectrum DX6, DX6i I think is a real common one in the classifieds used. You could buy them for 80 or 90 bucks. 6 channels will get you pretty far along. It'll do mode selection, it'll do GPS mode selection, plus your 4 basic flight controls. If you wanted to add retracts, that's another channel. So 6 channels will get you started. If you know you really want to do this and you're going to be doing it for a while, buy at least 9 channels. At some point down the road, if you can justify 12 channels or more, that's a decision you can make at the time. And that's outside the scope of this basics conversation. But I hope I've answered some of your questions. I hope I've given you an idea of how these work. And I hope I've helped you to understand a little bit about understanding how all the different components come together and how they relate to each other to make the whole system function as a usable aircraft. Okay? As always, if you have questions, come to multirotorforums.com. Get my attention, Scott's attention, soon to be Bill's attention. We'll help you to answer questions. If you saw people on here today like Patrick Roy, you have questions about the presentations they gave, come to the website and ask questions. The YouTube text below the video screen will have links to anything that was mentioned today. We'll also have that at the website. And that's it. Welcome to 2016. I hope you like the new studio. We're going to be back next week. Our special guest next week is Professor Javier DIEZ from Rutgers University. You might have seen his video of the NAVIATOR drone on YouTube. It's an octocopter, a coaxial quadcopter that flies and then dives underwater, and the propellers and the flight control system continue to stabilize and move the thing through the water. He's actually at Rutgers University, about 40 minutes down the road. He's coming here with some of his student assistants. They're bringing one of the NAVIATOR drones here, and it's going to be an awesome episode. I can't wait to see this thing. I've been in touch with Professor DIEZ. He seems like a nice guy. I think we're going to have a great show. So the next show is January 27th, 9 o'clock Eastern Time, coming to you live from our studio here in Clinton, New Jersey. Everything's archived on YouTube. We're always available, Multi-Rotor Forums. Thank you for watching. Appreciate it. Hope you enjoyed the show.